Hello, good day to you all. My name is Jared Ruckel. I'm a moderator here at InfoQ. I'm very excited to have a special guest for us here today, Tyler Jewell from Akka, talking about a really, I think, timely topic. Everybody's talking about, agentic AI these days, and Tyler and team will take us through it. The session today is titled Enterprise Agentic Architecture, Performance, Costs, and Safety in Production. So before we jump into this, I wanted to highlight a couple of housekeeping issues. Your lines have been muted, but we are very interested in what you have to say. So please submit your questions and comments in the chat in the GoToMeeting console as we go along here. You will also receive a recording of the presentation and the slides as well in email. So I think before we transition to Tyler, we can do a quick poll question just to kind of get a sense of how everybody's feeling about their agentic AI initiative these days. Can we bring that up? Yeah, perfect. So Tyler, I think this is always a great one to start with. Where are you on your agentic AI journey? So I think some of these things are really useful to understand where people are at as far as experimentation all the way to production.
Yeah, we're going to talk a little bit about some of the statistics on that have been reported on projects that have been unsuccessful. And I think that the media has certainly portrayed AI as being things that are failing, and really what we've seen in the many accounts that we're working with right now is that AI isn't failing. It's just that people are still in the learning phase. Call it prototyping, call it experimenting, call it whatever you want. It changes your whole mentality of how you need to design systems and think about them. And so it's going to take a while before people understand what it is and how they want to use it.
And I think even within the same organization, there can be different pockets of maturity. A lot of these very large companies have big development teams off experimenting, doing their own thing. So even within a certain organization, there can be a bell curve of distribution and maturity here.
Yeah, it looks like these results are these results visible to everybody in live update fashion.
Yeah, it looks like we've got about a third of folks that are still experimenting, about a fifth that are just learning, and there's actually a handful of folks that are actually in production, so a pretty good spread here.
Yeah, that's actually about a normal distribution, I think.
Fantastic. Well, with that context, why don't you take us through the content, Tyler, and we'll see how we do here.
All right, lovely, great to connect. Again, we're very interested in what you're thinking about, and please do post questions, and we'll get to them one at a time as we go through the presentation. So today, we're going to go through a few different things. We're going to spend most of our time just talking about what is agentic architecture, agentic system architecture. And then look at some of the systems engineering challenges that we've ran into in building agentic systems out in the marketplace. We're also going to take some time to talk about Akka. We have an agentic platform ourselves, and how we help you build and operate systems. We've actually landed a number of large-scale agentic AI projects, and we're going to walk you through what we've learned and what we've had to do with that. We'll leave a lot of time for a Q&A as well. And so with that, in case you're not familiar with Akka, where do we come from and who am I? I'm the CEO of Akka. And Akka is a 15-year-old company. It was started by our founder and CTO, Jonas Bonet. And originally, it was intended to be a development framework that simplified how you do concurrency on multi-core compute. And Jonas used some 1970s computer science called actors. And actors are a form of incredibly lightweight compute, as in kilobytes of overhead per unit of compute, that are managed by supervisors. These supervisors have the ability to deal with restarting actors, moving the actors around, and dealing with changing behaviors of those actors. And then they also had a mechanism of structured communication between actors that used non-blocking asynchronous message passing. And the combination of those things allowed you to build massively concurrent systems without having to know a lot of details around threading, asynchronous communication, locks, which 15 years ago, these were real big problems. And Akka grew into quite a successful project. Over the years, it's been downloaded over 1.5 billion times, and more than 100,000 systems have been built with Akka. Well, it turns out that the actor model, well, which really offered concurrency and resilience on a multi-core node, worked really well as a distributed systems framework, where you put instead of actors on a compute node, you have separate microservices that are operating across time and space over a network. And the actor model worked out really, really well for that. And so Akka grew into a system that truly distributed your logic and your data across microservices that will run in clusters out towards the edge or out towards close towards end users. And when you do that, when you start building systems that use a distributed systems architecture, you can unlock these remarkable SLAs and performance properties that you see here onto the left. And these are all our customers in various flavors here. And they've built a variety of different types of applications, everything from edge and IoT systems to retail transaction processing, payments processing. We're in 52 banks around the world, and all now increasingly a lot of agentic AI. And the reason that you can achieve these sort of remarkable SLA is that you're effectively pushing the data out close towards the end user. You're distributing it across the set of microservices. And what you're also doing is you're decoupling yourself from the cloud infrastructure. And these microservice clusters that you run out close to the edge, they are self-healing. And because they're self-healing, they can recover from hardware failures, they can recover from network disruptions. And since you're pushing your data out close to the end user, it effectively acts as a type of cache, if you will. It's actually something stronger than a cache, but by pushing your data out close to end users, you get remarkable read and write latencies. And so you end up with these sort of remarkable properties, and this is what Akka has been done for. So about a year ago, we noticed that we had a number of customers that were using Akka to do AI, and this was really intriguing to us. And we started asking them, like, what's the relationship between Akka and AI? And they came back to us and they said, look, hey, we've been diving into the agentic world. And in the agentic world, we've been really struggling with reliability and trust of these systems. And those customers at the time said, hey, a distributed systems approach and agentic AI might make a lot of sense to pair up and then to optimize for that. And we hadn't thought about it. We were actually taken aback a little bit by, what's the connection points here? What are we missing? And we started our process of really kind of diving in to assist our customers with the projects that they were working on, and learning a lot more about what an agentic AI system entails. And we're going to walk you through our learnings, and we're going to walk you through how we view this sort of architecture. But the interesting connection point is that if you think about a distributed system, and we'll talk about how Akka was designed, but the fundamental principle behind Akka over the last 15 years is that if you want to build a reliable distributed system, the Akka must assume that the environment is unstable, that there is no predictability in the hardware, in the network, or in user behavior. And so if the system anticipates or expects continuous disruptions, then the system is already prepared to know how to heal itself and to adapt on these changing conditions continuously. And so what's wild is that if you look at agentic AI is basically an application where you're injecting an LLM, and an LLM is incredibly unpredictable. It's a stochastic model. There's no way to know when it's going to hallucinate or how it's going to hallucinate. And so suddenly you realize, like, oh my gosh, if you're going to be building applications that make use of LLMs, it is a distributed systems problem, because you need to approach working with that agentic system as if it's going to be unpredictable and uncertain. Furthermore, it is also a distributed systems problem because as you're going to see, the whole point is to give agents goals, and there's going to be multiple agents that are running across time and space that are coordinating with each other, collaborating with each other to work towards these goals. And in order to do that, they're going to have to share information with each other, and they're going to have to coordinate with each other. Well, that's distributed coordination, and that's also distributed state. So building an agentic system is a distributed systems problem, with unreliable LLMs. So let's get into it. Let's talk about what is an agentic system. This is a reference architecture that we build up, and we're going to build this up into an interesting sort of narrative. So it all starts with an agent, and I think what's really good here is that you need to think about agents as a type of compute, type of a lightweight processing unit. And what it's going to do is that the job of the agent is to execute an enrichment loop that interacts with one or more models, right? But I think it's really important to know that an agent is a stateless function. It's basically a looping function. It itself doesn't have any memory. It doesn't actually have a lot of intelligence. It just basically is given a goal, and it's going to execute a type of loop to figure out an answer to this. And so the first thing that it does is it's going to need to have access to an LLM that it's going to invoke. It's going to invoke that LLM in a sort of a stateless behavior. Now, it passes a prompt into that LLM, which is great. That prompt has instructions, but the content of those instructions, the makeup of those instructions could come from other data sources around your enterprise. So this could be from a vector database where there are facts, semantic information about your domain that are stored. It could come from third parties. So it could be other APIs that you need to call, but it could also come from other agents. And so there are other protocols like A2A or ACP that you might need to call another agent in order to get some information. And very popular right now is MCP tools, which are a way for also basically to get more information or to execute an action, but all things that the agent might invoke. And so the agent has these sort of resources that are invocable by that sort of stateless enrichment loop. And what it does is it starts off by sending that prompt to the LLM or the SLM. The LLM can come back with a completed answer, or the LLM can come back with a, hey, I need some more information. Can you get this information from an API or an MCP tool? Or even like, hey, there's might be some instructions here to go invoke another agent. So the LLM comes back, and then the agent does its work, and it keeps going back and forth until there is a finalized answer, and it hasn't been interrupted. The agent needs to operate in a secure fashion, right? So every request must have an authenticated, it must be authenticated, meaning there has to be an identity associated with it. And then furthermore, because you're now in a system that is unpredictable, and you're focused on trust and safety, you got to trace every request. So you want to understand what the inputs were and what the outputs were. So you need to have an immutable record of that trace so that you can replay it or look at it for explainability purposes later on. And on top of that, you might need to do a guardrail or a type of, if you will, inline evaluation. And a guardrail is basically a way of saying, hey, is the input that I'm sending into this LLM safe? Right? Evaluate it. Is there any PII information in there? Is there any sort of hateful language, whatever that might be? And the same thing, you might need to evaluate the output. Is the output safe? Is the output accurate? Is there been any sort of malicious content that has been injected into it? Because it's possible to do that. And so evaluation is this process of looking at inputs and looking at outputs. And guardrails are the ability to control or block or alter the behavior of the agent based upon the interpretation that's there. So this agent's in this sort of enrichment loop, and it's going back and forth on a continuous basis. And what you do is, as you build up the system, the first thing is that you take in these inline traces these traces are all going to be persisted with your third-party observability or evaluation vendors. There are some AI specific or agentic AI specific vendors that have emerged that will take this. And they can do offline evaluation. So they'll look at your traces after the fact, and they'll kind of give you an accuracy score or a safety score. And some of them will do it inline near real time, but most of them are doing it kind of offline and after the fact. And so the trace and the evaluation, though, is also useful information for the agent, and that the agent can actually evolve and improve itself based upon its learnings from the previous executions that it does. So what you do is you also, in addition to sending your traces off to your third-party vendors, you take these traces, you take these results of the evaluations, and you put them into memory. And when you hear memory in the agentic world, it's basically just a database. It's just a persistent store, but it's a collection of things that have happened in the past that in aggregate might give you information that you want to use for prompting the LLM on the next go around. And so memory can be information that you have about the user. It could be like previous questions that that user has asked. It can be the historical trace. It can be other context information. It could be updating information from sensors from the outside world. But memory all comes together, and then you need to have some sort of algorithm that contextualizes all that intelligence in a smart way, so that the next time that the agent is asked to do something, it will go to memory and it will look at that as a data source of, here's some additional intelligence. I can grab that memory, I can inject it into my prompts. I can marry my prompt with information that's coming from my vector database or third-party APIs, and all of that together becomes a kind of an aggregated prompt that goes to the LLM, that gives the LLM the instructions of what it needs to do. There are third-party providers of memory, like Mem0. One of the things that you're going to see that's really cool about Akka is that you get memory for free. And that's part of the benefit of a distributed system. Since we can distribute state and logic all around the world across a bunch of microservices, your agent basically creates that memory object, and it follows the agent around and is available wherever it is without having to deal with persistence management. Now, when you get into an enterprise, this agent is also working off of not just a prompt, but there are goals and configuration that tells the agent how it should prepare its prompt, how it should choose the model that it wants to choose, whether it's for performance or cost purposes, and then also access policies. And these things you may or may not want them to be configurable. And so traditionally, when you use a development framework, you would just take a lot of this information and you would put it right in there as code, bury it into your agent as code, and you can do that. But you can also externalize that into an AI asset registry that allows it to be versioned and edited independent of the code that is running the agent, and then the agent can suck it in. Generally, everybody loves the idea of these AI asset registries, but what we found is that most of the really interesting agents that are getting built, everything is dynamic. So the choice of the model is dynamically chosen, programmatically chosen. The construction of the prompt, also the template can be dynamically and programmatically constructed based upon a bunch of variety. So so it's not as straightforward as here's a template and we're just going to use that indefinitely. Now, something needs to call the agent. So what tells the agent, hey, you should go do this enrichment loop here, and that's orchestration. And you hear lots of stuff about orchestration, and orchestration is basically just the ability to guide, control, and manage long-running processes. And so think of it as a workflow. It's a workflow that has a start, and it excuse me for all the ahs, but it has a start, and it could be no end, so it can have a very long running execution. Generally, these workflows have steps They could have sequential steps. They could have steps that you run in parallel. They can be finite state machines. They can be event-driven architectures. But it's really the manifestation of the behavior or the process that you're trying to achieve with this agent. You embody that into an orchestration, into a workflow. And so you would define these steps. These steps would have state. There would be very clear transitions from one step to the next. And within each of those steps, one of those steps could be, hey, I want this agent to go do this work and come back and give me a response. Now, since you have this workflow, the workflow can be running many steps at the same time. You can run the steps in the background. You can run the steps in parallel. And each of those steps could be going to different agents at different points in time. And so orchestration is a form of coordinating. You're coordinating the behaviors of multiple agents with different responsibilities towards a common outcome. And you're doing this in a durable way, in a reliable way, because you've embodied exactly how you want that behavior to occur. So that orchestration also needs to be authenticated, and it also is going to do its own inline evaluation, both its request that's going in and the response that's coming out. And so that orchestration creates a control loop between the agent doing something, the agent responding, and then continuing on that sort of iterative loop. And then you take it one step further in that what you're going to find is that these agentic systems, because they are stochastic in nature, the ones that you can depend upon are those that you need to have on a continuous improvement basis. And continuous improvement here is getting intelligence from the environment, gathering information from outside sensors, learning about your users, or even just getting events off of like a Kafka queue. But all of those things, IoT metrics, audio, video, user behavior, those are all things that happen on a real-time basis. They happen on a continuous basis, and so you got to do stream processing with that. Stream processing is the ability to process a chunk of data on a continuous basis without an end, and you need to do it in a way that doesn't overwhelm the system as a whole. And so what ends up happening is that you start gathering this sort of real-time intelligence. Perhaps it's a personalization use case or an IoT edge use case, but you're processing it, you're drawing conclusions from those streams, and then you either go and update the asset registry, update the agent memory, or even you can flag the orchestration. But one of those things, what ends up happening is that by continuously flagging or updating the information, you're creating a feedback loop so that the next time the orchestrator tells the agent to go do something, the agent has a different lens of what it had previously with that, and it keeps improving itself. And all of this needs to be accessible to outside systems, to third-party clients, and to humans. Humans might be participating in this system as well, and that's APIs. And so you have to expose these systems through authenticated APIs. There's a variety of different protocols that you need to support there. And these APIs can't just be REST or gRPC APIs. They need to be streaming APIs because you have information that's continuously coming into the system, and you have information that's continuously flowing out of the system. And so there's a kind of a continuous information flow through those APIs that happen outside the system. And all of that, the feedback loop, the control loop, in order for you to trust the system, it needs to be a zero trust network, so that the workflows that you build accessing the agents are doing it on a least privileges basis. The stream processors accessing the memory and the asset registry on a least privileges basis, and the agents accessing your vector databases, MCP tools or LLMs, least privileges basis on that. So, excuse me, apologies, allergies, that's human life. But all this on a zero trust network, because if it's a zero trust network, then you start the grounding of how you trust all this. And if you're in an enterprise environment, not so much a startup, you're going to find that there's this emergence of agent and workflow catalogs which will do a combination of things. One, there are so many different agents that start cropping up inside the enterprise landscape that you need to be able to discover them. It's not always as easy as somebody being able to just write those processes in. You need to have some sort of meta information about what those processes are doing, who's accessing the agents, how often they're accessing them, under what conditions. And then you want to start defining, okay, since this system is not deterministic, in order for me to build trust and confidence in the system, I have to start tracking metrics. I have to define organizational policies and guardrails, meaning I'm going to allow this system to continue to operate as long as it's within certain boundaries. But the moment it starts moving outside of certain boundaries, I need to alter its behavior, alter its guardrails, or just discontinue the work. And so this is the governance work. And so you see this sort of loop here of discovery of what the system is doing, and then the policies and controls being fed back into orchestration. And so all this comes together into a single agentic system. You've got the discovery, you've got the asset registry, you've got to have end-to-end tracing. It needs to be immutable tracing for auditability purposes. Everything has to be authenticated and authorized in a zero trust network. And then it needs to be continuously evolving. And so all of this makes up, an agentic system at the end of the day. And so, as we talked about at the beginning, there's a lot of media reports that are telling all of us that AI is failing. Our read of this is that most people are just not doing AI yet. They're learning, they're prototyping. Most organizations are trying to figure out whether there's a valid use case, what that valid use case might be. Can they trust that use case? Is it worth the cost? There's a lot of very interesting use cases, but the cost of running these things is pretty high. So is the trade-off worth it? And that's where most enterprises are at today. And when people have taken caution, we've seen that there are 3 barriers to adoption. One, as we kind of walk through, these agentic systems are not simple. They are complicated because there's just so many different piece parts. And it's easy to get started because there's lots of open source Python frameworks that will make it easy to go and build an agent. But an agent, as you've seen, is a small piece of the problem. There's just a bunch of other components. And so how do you get all those components, and how do you overcome that complexity? Obviously, if you don't trust the system, because it's non-deterministic, you're not going to put it in production. And so everybody, particularly as you get into regulated environments, are asking questions about, give me a set of controls or a process, if you will, that I can build trust. And then cost. I think that it's no surprise to anybody that the cost of LLMs have been higher than what you'd imagine. But the LLM cost is a fraction of what's happening. There's actually all kinds of shadow costs. And the real shadow costs here are that in order for an agentic AI system to continue on, there's so much pruning, maintenance, and ongoing, if you will, kind of tuning of the system, because you're constantly working towards improving its accuracy. That cost is really a hidden cost. It's a shadow cost, and it creeps up on you, and that you're actually in many ways spending a lot more post-deployment managing the system than you did in building it in the first place. So a transition a little bit into what Akka is. We have lots of great demos available online. We can follow up with some really fascinating demos. But what Akka is we have evolved from a development framework into a platform. And our platform now is focused almost exclusively on agentic AI. We like to think of this platform as solving the 3 problems. We've made building entire systems simple. And so we also have an approach where you can build continuous trust. You build up your trust very quickly with a form of continuous compliance. And then we overcome the cost problem because we can scale more cost effectively than any other approach to agents. And so simplicity, safety, cost effectiveness. And the way that we do this is that we give an SDK. This SDK is very simple to use, very easy to learn. In a matter of an hour or two, we can have you building very rich agentic systems with it. The SDK has a variety of components inside of it, and it's all the components that you need to build an entire system. So there's orchestrations for building workflows. There's agents in there, memory streaming. There's also APIs. So there's a whole API framework. So everything that was in that white box is in the SDK. And then you build, run, and evaluate those systems. When you build it, Akka, what we do is we create clusters of services. These clusters of services have resilience and self-healing properties built into them, and they are distributed systems. So your memory and your workflow state is embedded inside these microservices. And then you can deploy these microservices on any infrastructure, whether it's bare metal, edge, Kubernetes, Docker, embedded systems. We run inside of embedded systems. And so you automatically get all the properties necessary so that you can have elasticity. It's going to be very responsive with low latency. And because of the nature of the resilience, you get very high forms of availability. And so it's automatic. We build these things. You can then run them wherever you want. And then we give you a series of operating capabilities as well. We have cloud environments so that you don't have to deal with the operations setup and configuration of running a cluster. But then we also have operator consoles, developer debugging utilities, the ability for continuous evaluation and InfoSec controls. So all of this comes together into a single offering. And interestingly, we had talked about how like a year ago, we really started diving into this. And since then, we now have about 45 accounts in production. And some of these accounts are doing remarkable things with Akka and AI. Our largest account is doing 5 billion tokens a second of processing time. And I mean, to give you a sense, our understanding is that ChatGPT processes about 100 to 120 billion tokens per second. So we have a large customer that's about 1/20th the size of a ChatGPT, and they do this across 18,000 cores. So massive levels of concurrency, and that massive levels of concurrency are working across a half dozen models. And those half dozen models are very long-running, poorly executing engines, and Akka is basically doing a personalization and feedback loop on that. And we have some other really remarkable stories about work that's been done. We've got a medical transcribing client that processed petabytes worth of every medical journal on the planet, so that it could come up with alternative treatments and recommendations for patients and doctors who have diseases that could benefit from emerging opportunities. And so the pace of change in the medical industry is so fast that doctors and even specialists are unable to stay on top of what might be suitable for their patients at any point in time. And so this agentic system processes all this data on a continuous daily basis. And then they have 16 different agents that have been programmed, if you will, into different behaviors of medical specialists. And then they use their medical specialty and their expertise to make a variety of recommendations that ultimately filter their way back to the doctor and to the patient. And so had they tried to do something like that with petabyte levels of medical journals, it was going to take 9 months of time to process that with a Python framework. And so they needed to do something where the agents could do it in a massively concurrent way. And so Akka is well suited for that. So we talk about Akka, 3 things, and so we'd love to follow up and get you some demos, and we can give you personal examples and POCs as well. But we're just going to walk through a little bit about how Akka works. And the first is that we take this systems approach, and it's got everything in that white box in a single SDK. And because we take that systems approach, that single SDK, when you make a build, the binary that you create with Akka contains everything in that white box. And so you don't have to deploy a separate agent memory, a separate agent runtime, a separate stream processing runtime, a separate stream workflow. It's all right there. It's all defined in the application that you build. And that SDK comes with its own test kit and its own guardrails and its own evaluation framework. So as part of your build, you can run unit tests and integration tests and evaluation tests. And so you have a very tight inter-developer workflow with this that feels like you're back in computer science studies, all doing it on your local development machine. And then it's structured with this idea of maximal throughput, which is you want to be able to make changes, whether it's data changes or code changes, and minimize the change lead time, so that whether you're an individual developer or you're part of a team or you're in a multi-team organization, it's really fitting nicely into your SDLC, giving very structured golden paths, immutable artifacts, rolling updates, and standardized image packaging. So when you do a build with it, the binary that you get is effectively production ready. It's cluster from within. It's ready to deploy. And so you get a very kind of copacetic local development experience that doesn't need any modifications before it makes its way into production. And then because these systems, because there's so many organizations that are not trusting these systems, you got to get it there safely. And what we've learned is that to trust an AI system, you got to work through like this sort of 6-step process. And the 6 steps is, none can be skipped for what it's worth, right? You got to have a mindset of understanding this even before you started developing the agent. And if you can bring this in at the beginning of the project, your project is going to be on a great path towards success. And so the real interesting thing with this is that oftentimes with a lot of enterprise systems, historically we saw that observability was one of those things you start thinking about as you get closer to production. And in this particular case, you got to start with AI governance. You need to start with metrics, policies, and controls. Because if you can't define the policies and controls that you want for this agentic system, then you probably don't understand what you want it to do well enough. Now, those policies and controls need to make their way into metrics that are automatically tracked with your agent. And then you have to be able to define policies, not just externally, but policies as code, and then guardrails and evaluations as controls. And we have all those mechanisms. Like when you can build agentic systems, you can build those with Akka as well. You got to have a zero trust network. And one of the benefits of using actors in this case is that there's a lot of paranoia right now about if you use a general process for running your agents, those processes are attack vectors. And they're not necessarily isolated. If they have open ports, they have accessibility, then the agent can be compromised on that. And so one of the beautiful things that we found with Akka is that because of the nature of the actor system is impenetrable at the end of the day. And so it creates the foundation for creating a zero trust network, if you will, where you're going to have multiple agents collaborating over time and space. It's got to be able to recover from any sort of failure, hardware, network, or even LLM failures. And so in order to do that, you're going to need to have durable events. You're going to want to have a historical record of everything so that you can replay it. And in our particular case, we also give you multi-region active replication so that your agent context and their memory can be replicated across multiple locations for further reliability. And then there's a lot of paranoia about do agents take on identities? And so while agents are stateless systems themselves, the agents are invoking third-party systems. And so you do have to be able to pass along appropriate credentials on that. And then you have to have policies on how far those credentials are going to propagate. Do you allow them to propagate into the MCP tool, or do you allow them to propagate into another agent that you have? So all connections, all user all human users, all agent interactions, and all tool interactions, and then all interactions with third-party systems have to be verifiable. So you want origin-based policies, a very structured role-based access control and IAM system there. We talked about how important it is to trace interactions. You got to have a record of every interaction. It's not just for explainability purposes, it's also for auditing and chain of thought journals, which become important when you're asking questions after the fact. And then we talked about the importance of continuously improving. And so build trust from the beginning, and the system is going to be more likely to survive. And then scale cost effectively. And this is one of the things where with Akka, we're so proud of everything that we've got here. But because of the nature of our actor-based concurrency, we are able to take those entire systems that you run, and we can do them on a shared compute model. And so that means you eliminate databases, you eliminate the need for like a Redis cache, and you also eliminate the need for having to run silos of different application servers. One for your agents, another one for your workflows, another one for your stream processing. And so you eliminate all this sort of overhead, and you can get like 90% density. So much so that we have, information that shows that, like one core of Akka will give you all the sort of computing power that would cost anywhere from 5 to 7 cores with LangChain on Python. And so those extra 5 to 7 cores are going to add up to almost $2,000 a year in cloud compute costs. And so the savings really do add up. And you do need to scale this stuff effectively. I know that a lot of people are so focused on the cost of the LLMs that are like, hey, it's going to cost me millions of dollars for the LLM. What do I care about the cloud infrastructure? But it all matters, right? Because you got to look at the total cost of ownership for the system as a whole. And so all this comes together into system architecture. And so we kind of want to pull it all together on this. And so you're going to have in an enterprise, you're going to have your systems of record off to the lower right. And those are going to be accessible over API gateway. Those are your enterprise APIs, or maybe your analytics databases, whatever they may be. You're probably going to have some sort of message brokers, which are streaming integrations to other systems. It might be the way that you're pumping in information from the outside world, whatever that might be. There could be IoT metrics that are flowing through there. And those Kafka systems might be running inside your VPC, or they might be outside the world. And then depending upon the type of agentic system that you're going to do, you might do a vector database. A vector database is a way of storing facts, very kind of a structured facts, which is semantic information about your domain. And you might stand up a vector database for that. It might be files, it might be drives, whatever that may be. And then you're going to need your models. The commercial Foundry models are just those off-the-shelf models where you can hook up an API and call it over the internet. But in any sort of reasonably sized implementation, you're probably going to self-host the models. The cost performance is just it's just so obvious in that case. And so in that particular situation, you're going to have SLMs and LLMs, either ones that you've downloaded and tuned, or ones that you've created yourself. And they're going to be running on some sort of GPU farm that you have. And you have an LLM proxy there where the self-hosted models will probably have the option to go to the Foundry models if for some reason they're unavailable or the cost makes sense. So you can have a proxy to broker it out there. And so these are all the sort of third-party systems that you have. And like with Akka or your agentic system, you're probably going to stand up some sort of cluster of agents. Now with Akka, you get your orchestration, memory, processing, and MCP service all included, including your APIs, and you run it as a cluster. You're going to put this in your VPC. You're going to probably then front that cluster with an authentication mechanism using ACLs and JWTs as an authentication mechanism there. And then you're probably going to front that with an API gateway. And your clients, your internal clients, are going to have access through that API gateway. And then you're probably going to have other agents, and you're going to run those other agents as a separate cluster. So each agentic system gets its own cluster. And those agent clusters can talk to each other over brokerless service-to-service messaging. You can do A2A or ACP protocols. That also needs to be a zero trust network. And you might start layering in clients that are outside your VPC as well, that are still going through the VPC. And as you've noticed within this agentic region, the agents have had access to the models, to the commercial LLMs, the vector databases. Kafka could be streaming into the system, and this system has access to the API gateway as well. And so since you need to be developing these things on a continuous basis, oh, I apologize. And in particular, sorry, I skipped this part, but ending with Akka, Akka offers an automated ops option where we will manage all of that for you on a managed Kubernetes if that's what you wanted to do. But then you wire in this system, your runtime system, and you want to be able to deploy to that. And so now what you do is you wire up your SDLC tooling to your agentic system. And the first thing is that AI-assisted DevX has come such a long ways. Like when we show you some of the demos and we kind of send you a bunch of stuff, we can build entire systems using Cursor, Windsurf, Claude Code, Gemini, CLI in a matter of minutes. The AI-assisted DevX that we pump into this knows the SDK to such a degree of intelligence that it generates these entire systems, oftentimes without making any mistakes whatsoever. It's really quite stunning. But it generates code. You're going to save the code in a repo. You're going to take model tuning and move that through model CI/CD. You're going to take the agentic system code, run that through agentic CI/CD. And in our particular case, with these binaries that we create, we put them into a regional registry. Think of it like a Docker registry. And then that registry is the staging location for deploying the clusters into the runtime environments. And just because we focus on these sort of enterprise properties with HA and DR, Akka gives you the ability to actually stand up separate regions. You can have multiple regions. They can be in any cloud provider you want, AWS, GCP, wherever that may be. But when you have multiple regions, you end up deploying the same application into each region, and we will automate the replication of memory and basically all the data that the systems depend upon. And then there's also failover and disaster recovery mechanisms between regions. So you can use this to build systems that are multi-cloud. You can use this to build systems that are running in different availability zones. And you can use it to build systems that have data sovereignty, where you have some regions that only have access to certain data and other regions that have access to other data as well. So all this comes together into a uniform system. And in order to get, in our particular case, in order to do multi-region deployment, multi-region HA and DR, we use our federation plane. And the federation plane is something that runs at Akka.io. And that is a central coordination point, if you will, that coordinates regions across the world. The federation plane is not necessary for the safe execution of the systems in your VPC. It's only necessary for this sort of kind of cross-region coordination. And so all this comes together, and we're going to open it up for some Q&A here. Is what we've seen is get the engineering right, and the AI will work. Think about trust and governance from day one. Iteratively improve, so your continuous improvement here. And then you do have to let go of this idea that the system's going to be deterministic. It's a hard thing to let go of, but what you can do is you can build systems that you have a very strong expectation on certainty. And so you do that by building these layers of the certainty. You have kind of multiple layers of controls, guardrails, policies in place, and the system over time will start to feel deterministic and meet your expectations. And so we're running there. We had a demo set up, but I'm worried about us running out of time. And the demo provider is, I don't see quite logged in yet, but we can send along the demo that we were going to do live. We have it recorded. It's nicely available for anybody who wants it. But Jared, why don't we open it up to some Q&A here?
Yeah, fantastic. Thank you, Tyler. And folks, please do submit the questions that you have as a result of the presentation. While we're waiting for some of those to come in, Tyler, there's a couple that kind of stuck in my mind as you were going through this. How do people, how should they think about getting started with a project? Do they need a clear use case to get going, or what have you seen actually work well in the field?
Well, everybody's kind of looking for use cases, and and I think that what's interesting is agentic system reasoning is really uh, you're no longer a systems architect; you become a reasoning architect. And
Mm,
I say this because a reasoning architect thinks differently than a systems architect does, and the only way to teach yourself to think about reasoning problems is to start experimenting with them. And so it wasn't until we started building agents and basically trying to task them with different kinds of challenges that you really understand the problems of, okay, what is the agent doing? Okay, how do I then compensate for this sort of weird behaviors that's going on? And so it's really no longer about what the code is or how the system architecture is going to look. It's really about what's the reasoning architecture I want and how do I coordinate all this sort of information to work towards that goal. So just get into it.
interesting.
Just start prototyping, and you'll start acquiring these skills.
Yeah, makes sense. And speaking of skills, are there any kind of prerequisites that people need to have to get up and going with this? I mean, there's some intellectual curiosity, of course, but as far as the technical stack or skills that you need to bring to bear, what are you seeing inside your
Oh,
organizations that are most mature with this?
the first thing is you have to have curiosity and
Yeah.
a brain, brain's kind of useful here. And if you can start using Chat GPT to just start asking questions of a more complex nature, then that is everything that you need to start building agentic systems. There are now what we're tracking well over 100 different frameworks for building agents that are out there. Some of them are low code, drag and drop things that you could start using. Others are more professional code systems like ourselves. But even with Akka, as long as you have a really simple Java understanding, a really basic understanding of Java, that's everything that you need to start building these systems. And if you go to our Getting Started guide, in about 5 minutes, all it takes is, as long as you have Java installed, you'll be able to build, run, and start interacting with multi-agent systems without knowing really any sort of code. And the AI assistants are now so good that even if you don't know how to program in Java, you can tell the AI assistant, hey, you basically give it the context of how Akka works. We give you this file that you load into it, and then you can start asking it questions, and it'll generate systems. And so you can start learning the code by just seeing what it generated.
Yeah, and it's interesting you mentioned Java. That's been the number one enterprise framework for quite some time. It doesn't always get the attention or credit it deserves for this type of this type of work. There's Python and others there, but it sounds like Java has a surprising number of options.
Java. I think that most people associate AI with Python, and I think that there's actually a lot of interest in that. But and I think that happened because Python is actually a great language for doing model training,
Hmm.
and because it was the language of model training and ML ops. Now that Agentic came onto the bear, where it's AI infused in your applications, a lot of those early requirements were passed along to it must be the model guys. It must be my Python team that needs to go build those agents. And so all these frameworks emerged in Python to start building those agents because the model team started to do it. But the issue is that almost all those frameworks, they don't have the reliability, the resilience, or the performance and the security. And so now what's happening as more and more agentic systems roll into the enterprise, the CIO is raising their hand and saying, like, wait, if there's going to be an SLA associated with this thing, we can't abandon the 20 years of history that we have on what it takes to build resilient systems. And
Right.
most of the accounts that we're winning, and we're winning some big accounts, they're just like, we got to use Java because of all the stability. And in a lot of ways, and so now there's been a bunch of really good Java frameworks that have come out, and I think you're going to see a huge wave of adoption in the Java. There's Spring AI, there's Embable, there's there's a Kotlin framework. I'm blanking on the name. There's the Google ADK, but Akka here, and basically it's Kug from Kotlin. But Java not only has a bunch of frameworks that will come out. I actually think that within 12 months, we're going to see way more adoption with AI in Java than we'll see with Python because of the CIO pulling it into their organization.
Yeah, interesting. Well, a prediction for the year ahead. Thank you. Question here from the audience about FedRAMP. How do you think about the authorization there for public sector deployments?
So FedRAMP is interesting. We have a number of customers who are FedRAMP compliant accounts. So the beautiful thing is with Akka, the clusters the binaries that we build and the clusters that you run can run in air-gapped environments. So Akka is incredibly well suited for already running inside of any sort of FedRAMP environment. And I think that that's important because you need to be able to create agents that are completely isolated. And so that, if you want to be in a FedRAMP environment, so you got to be able to install them, deploy them, and then execute on a completely isolated basis. So that gets back into the 6 stages of how you build trust with the system. We'd also love our own managed environments, the ones that we run inside the VPC for you, to eventually get FedRAMP certified. We're kind of going down that path ourselves, but we have an answer. You can run Akka without our managed service, but that's how we look at that.
All right, fantastic. Well, that's about all the time we have here for today. Any closing thoughts, Tyler?
No, I think that everybody's still in this learning and prototyping phase. Keep pushing the envelope on that. We're excited to see what people want to do next. And if anything we said here today was interesting to you, reach out to me personally. We'd love to talk to you about what your project is.
Yeah, fantastic. And in the spirit of continuing that learning journey, there's a ton of fantastic information at akka.io. There's sample apps, there's demos, and then the SDK as well. So a fantastic set of information there. And considering what y'all have been doing in distributed systems for quite some time, Tyler, it's not surprised there's a bunch of great stuff on your site there. So on behalf of InfoQ and Tyler, I'm Jared Ruckel. Thank you so much for joining us, and we'll see you next time.
Thank you.
Take care.